Yeah, so let's start. Do you have any questions? Okay, if no, then let us talk a little bit about Laplace equation, namely about the properties of its solutions. So there is so-called maximum principle. Which states that if we have some harmonic function, harmonic function is a function satisfying the Laplace equation, Laplace sin of f equals to 0. So, uh, yeah. So if you have this, then a maximum of and so f of some x. And then maximum or minimum of this f is always for x in some domain D. Then maximum or minimum of this function is always at the boundary. And maybe even more useful statement is that we have not only this, but we have a statement that a value of our function in some point x equals to the average of its values over the sphere. So 1 over volume of s d minus 1 of radius r integral over the sphere in this. So we have some point encircled by the sphere, and so this sphere is centered at point x. How do you know this? Like this. But it's clear, right? Uh, mm, so let us put here some x prime. So x prime minus x, prime minus x equals to r, the sphere. And if you prove the statement, then we see that maximum cannot be inside the domain, because otherwise it will be greater than the average value of this function on this sphere. So, and so. And do you have any ideas how one can prove such a statement? No. If you are talking about the statement that maximum is the boundary, then yes, of course. And so, no. This so it is a kind of intermediate step in this proof. To say this, we need to know somehow this statement, and this statement follows from a Laplace equation. So, mm, so you propose to integrate something over the internal part of a sphere, right? Or what? Mm-hmm. But what precisely? What kind of expression? Mm, mm. So, mm, hmm? Uh, it is. So the idea, the first question is how to obtain this. So it should be some equality between integrals, and we would like to have f of x obtained as some integral, and it should be the integral with delta function, right? So let's write that f of x equals to the integral over over this ball of radius r, d-dimensional, or d dv. So it is d minus 1. Here is d delta of x prime minus x f of x prime. Right? So and now how to construct this delta function? We can write an integral of yes, so we can write it this way. So this way we get delta function, and we get f of x. Then we can integrate this by parts, saying that it is. Or we can, so this integration by parts can be written as dv d over this domain of gradient of gradient of g times f minus gradient of f gradient of g. Right, and then we can integrate this over the boundary. So this will be. Hmm? No, this is over the whole volume. I've just written this expression identically. Then let us let us integrate this part using this Stokes theorem, or how it is called. So the theorem that integral of the other is equal to the integral over the boundary of this ball. So it will be an integral over the boundary of d normal times gradient of g times f minus that integral. by parts, maybe let us write it just here. So we can write that it is regardless of G. So right, Laplace acted on G, and the one acted on F. So it will be gradient of F times G minus Laplace and F times G. Okay. So, but on this last integral equals to 0, because Laplace and F equals to 0. So we have integral over the boundary d r d dn gradient of g times f plus sign of the minus sign of this integral. But this given function can be shifted by a constant, because we simply need this to satisfy plus one equation with delta function on the right hand side. Or we could, yes, so we can shift it by constant, and this equality holds. The consequence of this is that this integral can be made 0, and this integral vanishes independently. So this integral is 0. So we can write. So G can be shifted by G plus constant. So this integral. 1. We can put because this green function is something like minus 1 over minus some c that depends on dimension divided by r to the minus 1. And we can simply put here plus so put it like x minus x prime to the minus 1. And we can simply add here cd over over r to the power of minus 1. One second. If this holds for any c, and then this integral over the boundary vanishes independently. Then gradient of f equals to 0. So when we put g equal to 0 on the boundary, and then this quality becomes simply f x equals to an integral over the boundary yeah, gradient of g times f. But since green function is radially symmetric, it is 1 over, sorry, it is not d minus 1, it's d minus 2. Since the green function is like this, then this integral equals to the integral of dn, some like d minus 2 c d over x minus x prime to this is proportional to n. So x prime. So and this is constant. It equals to r. So it is the integral over d over the volume element of the sphere d minus 2 cd over r to d minus 1 f of x prime. Now, in principle, we could look for this constant, but you know, this formula should hold, for example, for the constant function. So all this combination of constants should give 1 over volume. So the answer is 1 over volume of the sphere of s d minus 1 integral d minus 1 from so is it okay?
Just can you repeat that equal?
So here we see that the power of radius is the same as in the volume of this d minus 1 dimensional sphere. So its volume is proportional to r to some power d minus 1. So this so the answer will be kind of radius independent. And we know that so the only unknown is the exact value of this constant. But we know that if you substitute here x equals to 1, for example, this equality should hold. And this way we can fix that constant. So namely 1 constant will equal to 1 over volume of this s d minus 1 integral d to the d minus 1 1. And I understand this constant that appears in the n function is related to volume of d minus 1 dimensional sphere. And this is one of actually one of the ways to find it.
Yes, but I don't understand why in the denominator there is the absolute value of x minus x prime to the d, it becomes r to the d minus 1.
Because there is x minus x prime in the numerator. So I used the formula that the gradient of f of x minus x prime should equal to x prime over absolute value of x minus x prime times f prime of absolute value of x minus x prime. Because it can, so it is formula here.
Yes, no, is that
power is because we are differentiating this function. So we get d the power becomes on this negative power becomes bigger. And another power comes from the fact that it is x minus x prime over, so I can write it like this, d minus 1, absolute value of x minus x prime. And altogether, because then normal vector pointing from the center of the sphere. So this is this normal vector. Yeah, and then it is n. And this this dn in here it is n times d minus 1.
Okay.
So we multiply this normal vectors. So when x is 1, so it gives us just this volume element. So,
Thank you.
and so there were two ways to compute this constant. One was to do this full Fourier transform, to go from the heat equation, for example. And this method knows nothing about d-dimensional spheres. Another method is like this. You can say that this gain function is some r to some power. Then we do computations like this to check that it solves well, basically to find this function, to find to first find this power dependence, and second to find the value of this constant. So this way we see that this constant is related to the volume of S d minus 1, and if we know this constant, then we know this volume of d-dimensional sphere, which is not obvious, as it is one of the methods to find the formula for this volume. Okay, are there questions about this? Okay, so we have this statement. So we know that maximum is achieved on the boundary. And let us, and also it can be understood in a different way. So, for example, if our function achieves maximum somewhere inside this domain, and it is actual maximum, then all its second derivatives should be either positive or negative. So if it is maximum or minimum. But if it is true, no, not all. Second derivatives, saying something stupid. It's Hessian matrix should be positive or negative definite. But at the same time, we can write that Laplacian of f equals to sum of e I times Hessian of f and ej. And this equals to 0. And if it is positive or negative, it should be either positive or negative. So which is possible. So this can something else should be said here, or it's enough. But if you do in this way, we see much more than just this fact. We see this equality of function and average value of the speed. Maybe it is a little bit more interesting. Okay, any questions?
Okay, but there should be the same. There should be like equation of f times ei scalar product ei.
Oh,
The same
yes,
units.
sorry, yes. Yes.
Okay. Okay.
So if it is positive or negative definite, this should be either, so each term should be either positive or negative. So, and it contradicts to the fact that there is some equals to zero.
But this doesn't prove that. Okay.
Yes. So here the thing that yes, it can definitely it cannot have a simple minima and maxima because of this property. But if this vanishes, in a sense, if all second derivatives vanish, then we don't know what to do. We need to do such kind of proof. So, yes, so this argument works only if we assume that all the minima and maxima are isolated. And maybe it's no, it's not even about isolated or non-isolated. If concern is non-determinate. So it's not even a property, it's just an illustration of how, why this is prohibited. So there is an application of this. Any other questions? There is application of this to complex analysis. This proves that there are no holomorphic functions on compact manifolds except constants. So if some function is holomorphic or anti-holomorphic, if for example the bar f equals to 0, it gives us automatically that the bar of f is equal to 0. So, and if some manifold is compact and it does not have boundary, then this function cannot have minimum or maximum, so it should be constant. Sorry, compact. So in particular, if we consider CP1 instance complex sphere with infinity, so functions so it is a compact manifold. Or there is this clause, which we studied the last time, which can be represented like this. 1 tau, 1 plus tau. So this should be identified with this, this, and this. By the way, last time we obtained theta 1. So there was a function theta 1. And the question is, what about this? So this was a function that was given by some convergent series, and it had zeros at 0, basically in all these points in all these places. Does it contradict this theorem or not?
No.
Why? So what can we say about this?
Maybe I don't remember very well, but the 0 point of theta 1 are on the bound, not the boundary of the lattice, like
We can shift it by 1/2.
yeah, the zeros were on the lattice, right?
Yes.
And if we identify it, like vanishes, yeah, like disappeared the 0 and remains just the inner part, maybe.
Oh, we could equivalently shift this fundamental domain and say that it is from minus 1 plus tau over 2 to 1 plus tau over 2. So then 0 will be here. 1 minus tau over 2 is tau minus 1 over 2. We can draw it in this way.
Okay.
No, the point is not here. The point is that it is not a function on this torus because there was first this problem as equals 1 tau equals to minus theta 1 of the tau and the second theta 1 of the plus tau was something like e to the I forgot precisely something like this probably. So it's not a function on a torus.
You mean that on the lattice the function is not well defined because on a side takes a value and on the other side another one.
Yes, it is multiplied by something.
Okay.
And so it is not a function, it is a section of some line bundle of this torus. If you want to construct the actual functions, we will need to write something like this. Product of theta is plus from I equals to 1 to n, from 1 to n, theta 1 of z minus ai, tau over theta 1 of z minus nzi, tau, and this and we should also have one condition that sum of ai's equals to sum of bi's. If we satisfy this condition, then we will cancel all this periodicity prefactors. And so there is consequence of this formula that, for example, if you ask this function to have only one pole, it is impossible. It can only be constant. But functions two poles and two zeros already exist. But all such functions are holomorphic. They have a pole and they have zeros. And as it should be, the only constant functions, the only holomorphic functions are constants. So, and the same for the sphere. If you ask some function to be holomorphic everywhere except infinity, then it will have either some order polar infinity or some central singularities. For example, either some polynomials of z or some e to z, az, something like this. That's quantity wise. So, and this is actually, so all this is very, very simple, but it has very powerful applications everywhere. These applications are all based based on the fact that if you manage to construct two different objects in some different ways using different techniques and prove that their ratio or difference is holomorphic function, then it will mean that it is actually a constant. And if you compute this constant and find that it is zero, then you know everything. So, for example,
Sorry, just a question. It was also yours that if I have an holomorphic function, it has the same number of zeros and poles. Also on the locus.
Yes.
Okay.
And this is the fact that it has the same zeros, number of zeros and poles can be checked by example, by integrating d over f. So this formula is a kind of formula that any holomorphic function on the sphere can be written with the ratio of monomials. Here we represent monomials by theta functions. What are the possible applications? So, for example, let us try to compute this infinite sum over n integers 1 over z minus n. So the question is, what is the value of this sum? You can group this terms so that you see that this sum is actually convergent. You can write it as a sum of z over 2z over z squared minus n squared. So it's convergent for any z. For n equals to 0 to from n equals to 1 to infinity, and here 1 over z. So this convergent, so it defines some function that is analytic everywhere except this point. And this function is such that it has first order poles with coefficient 1 in all integer points. Let us call this f of g. And let us study the defects of f of z minus f of z minus tangent of phi z. So, the question to you, what is the asymptotics of this function at z equals to 0? Or at z equals to 1 or at any integer point? So when z goes to n, let us put z equals to n plus epsilon. F of n plus epsilon minus phi tangent will be 1 over epsilon minus, so cotangent is pi periodic. So we can simply arrange this by n. And then it is, so it is pi cosine of pi epsilon over pi epsilon. And so this is orthogonal 2 we expand cosine in the periodic series is 1 over minus pi squared epsilon squared over 2 plus something. Then sine pi epsilon minus we can write it, but we don't need the next term. So it's also 1 over epsilon. Alright. Is it okay? So now, so it is regular. So and this way we cancel all possible poles. So this this function is holomorphic. And the only thing to check, well, so actually to say that this holomorphic, we need to check what happens at infinity. But for example, here we see that all these terms go to 0 and go to infinity. And we need we need to check what happens on this tangent. When z goes to infinity, and let's choose some convenient infinity like I infinity. So 0 minus I want to write the definition of sine and cosine in terms of exponentials. To the pi I z minus plus e2 minus pi I z over e2 pi I z minus e2 minus pi I z. In the limit z goes to I infinity. So, and if we do this here, then plus or actually, no, we cannot, no, it was a mistake. We cannot say that this z is, that z goes to to 1, to 0, we need to compute something. So maybe let us actually better study behavior of this function at some point like z equals to 0. Let me think. No, this expansion at infinity. No, probably it is also doable. Again, didn't think about possible problems with this computation. So. So this term behaves like this, it is clear. But let us see what happens with this sum. Well, this sum can be approximated by integral. So, so the first term can be neglected, and the sum it is an integral from n from 0 to infinity to z dn divided by z squared minus n squared. Squared minus n squared. And z is imaginary. So, we can scale this so let us say that z is I so it goes to plus infinity I times a and a is b. So when z goes to infinity, this integral goes to what value? All this expression. What does it give?
Minus pi I.
It is so it will be minus pi I, and here it will be minus minus 2i a integral from
Maybe from 1.
but no. This n, I've already scaled this. Oh, okay, no, we can write from 1, but then this a will go to infinity.
Yes. From infinity.
So, so here I have 2a so from 1 to infinity dn over a squared plus n squared. So it is minus pi I. So actually, did I make some mistake here or not? Maybe it is it should be fine. No, wait. You said that it is minus pi I, but when we send z to infinity, then to plus infinity, this terms survive, and there is also minus factor here. So all this factor gives pi I, plus plus n.
From what?
Because these two exponents go to 0 when z goes to plus infinity. And this go to infinity, but one enters with plus sign, another with minus sign, and there is overall minus sign, which comes from the fact that there is a type of sign. this ratio goes to -1, and is multiplied by minus pi I.
If I like so if like I'm computing it in this way. If I um, write that like e to the pi I z times 1 plus e to the minus 2 pi I z this and over e to pi I z times 1 minus e to the minus pi I z minus 2 pi I z, like in the parentheses I get 1 and 1.
Oh, okay. So what is the limit of e to the pi I z when
And no, that vanishing with the other below.
So this two vanish.
Yes.
And this two
Go zero. Go to 0.
No, this two go to infinity. And this goes to 0.
No, no. The first one vanish, right?
Yes.
And the second one go to 0 when z go to infinity.
No, what is the difference between vanish and going to 0? So,
Yeah, I mean,
e to the pi I a is equal to minus pi a. E to the minus pi a equals to e to plus pi a. So tangent of minus tangent of I equals to minus pi I e to the minus pi a minus e to the pi a e to the minus pi a plus pi a. So we receive the term which is as it goes to infinity. So let us write it like this: pi a 1 minus e to minus pi a 2 pi a 1 plus e to the 2 pi a minus 2 pi a.
yeah, okay.
And a goes to
You're
s.
right. Because okay. Yeah, because you do the change of variable. Okay.
Actually, I just realized that we don't need to do this computation because this function is odd. So we could simply say that it is 0 because there are no constant odd functions. But once we started this, we can just finish it. Here I can scale z by a and get that it is 2 times 2I times pi over 2. So it is 0. Sorry, I should have noticed that in the beginning and did not compute this integral. This way we found that we have the series for the tangents. Are there any questions about this? other statements. For example, you can find how to compute so-called zeta values at even points. In a sense, you can learn how to compute sums of 1 over n to k. So, this right hand side 1 over z plus sum over z over z squared minus n squared. So this can be expanded at z goes to z goes to 0. So it's 1 over z plus sum over 1 over z minus sum over 2z over n squared over 1 minus z squared over n squared. So it is 1 over z minus 2z over n squared plus sum from 0 over n squared, sum from 0 to infinity z to k and to the to k.
The sum or the n before?
Yes, thank you. From n equals to 1 to infinity, from n equals to 1 to infinity, and here we have sum from for n equals to 1 to infinity.
Before the oh, that makes sense. It shouldn't be before 2 minus z.
Yes, thank you. Yes, 2 z, and here we have 2k, so here it's z to the 2k, and to 2k plus 2. We see that so if you note the sums as sum of zeta of s, which is a sum of 1 over n to the power s from n equal to 1 to infinity. And if you write it here, then it gives 1 over z minus sum from k equals to 0 to infinity z to k plus 2, k plus 1, zeta of minus 2 minus 2k. And this equals to cotangent of z, of iz. So if you compare this to sides, you can find some formulas for such sums. Otherwise, it would be not very clear how to compute it. So, for example, we can find from here that sum from n equals to 1 to infinity, 1 over n squared equals to pi squared over 6. Sorry, I wrote so many two plus two, please. Sorry.
And also maybe a 2 somewhere.
Yes, you are right. Yes.
Okay. Sì, c'è ragione. Maybe she's saying that pi is equal to pi cotangent of pi z.
No, could you say it again? Yes.
Because also there in the
Yes,
formula.
thank you. Yes, you are right. So it's one application. Another application is that we can integrate this formula. So we can integrate this integral in dz phi increment phi z equals to what? It is d sine of pi z divided by sine of pi z. So it is a logarithm of pi z. And the integral of the right hand side of this. Actually, maybe it is better. It is better to integrate from some distinguished point, for example, from 0 to have the constant immediately. So let's compute this integral from 0, and let us subtract here minus 1 over z. So in this way, it will be so. I also missed sign minus g minus d0 over t. So this will equal from 0 to 1. And this will equal to d log of phi d log of sine of phi d over z. Like this from 0 to 1. Let us actually write like on this. Oh, no, wait, from 0 to 1 to some point z. It should be the integral from 0 to arbitrary point. We can compute its value in the lower limit. It will be the logarithm of 1. So, which is 0. Okay, so our main discussion is the logarithm of sine phi z over phi z. And now let us do with all these terms, except the first one. Let me go from 0 to z, sum from n different from 0 of this guys 1 over z minus n dz. It will be a logarithm of z minus n from 0 to z. So there is its value at the lower limit, which is a logarithm of minus n, and value at the the logarithm of phi. From n equals to 1 to infinity. 1 minus z squared over n squared.
No, perché il quadro anche perché
No, perché è sommità, sì.
bravissima.
Sì,
Però
poi ci sono.
maybe the first logarithm, no, the second one, the sign, the it shouldn't be like z over n minus one.
Why minus 1?
No, è perché il meno che ha fuori poi l'ho usato per.
No, perché quello non sarebbe.
No, aspetta.
Should be like logarithm of z over n, logarithm of z over n over n.
Originally
Ah no,
I write
aspetta,
it
perché
as
quella lì è due estremi.
Ah, vabbè,
E c'è il meno n che poi.
Io lo posso mettere al contrario.
Secondo me tipo interpretandoli insieme riesci a togliere quello del meno. Secondo me sì. Cioè quando lo compri di zero.
No, ok,
Yeah.
yeah.
E hai meno n che va sotto.
Però.
E quindi cioè tu hai
Sono d'accordo.
così
Ah, tu
punto di A più questo è quello in Z e poi hai meno meno n, cioè
no, forse.
magari
No. I agree here. Not that one. I don't agree. Maybe the series of log of 1 minus z over n. You are like switching them. You get z minus n and the logarithm of z minus n and the logarithm of minus n. Oh.
yes.
You're switching them.
Yes, so I basically divide everything by minus n and get 1 minus z over n.
Because if you compute the logarithm of z minus n between 0 and z, you get the logarithm of z over n minus 1. Do you agree? If you compute the logarithm of z minus n between 0 and z, you get the logarithm of z over n minus 1.
No, do I agree with this expression?
No.
No. It is the logarithm of the minus n.
meno n di n fa 1.
Ah, yeah. Sorry, you're right. Yeah, sorry, you're right. Sorry. Grazie.
That you're following me right now. All the mistakes are fine. Because if I, for example, try to track some signs in the formula, then I realize that in memory I can store signs that as 3 or 2 bits. If there are more than 3 signs, then it's probably committing one half I won't make a mistake. But now this is that we computed this the integral of the left hand side and the right hand side, and we can write a formula that as sine of pi z sine of pi z equals to a product z equals to product z times z times pi z times product from n equals to 1 to infinity 1 minus z squared over n squared. of this network images, especially when the number of images is big, it is it is like equivalence between the two formulas. One formula is obtained by some analyticity requirements. For example, we were looking for some given functions that have logarithmic singularities at prescribed points and are periodic. Another method is to simply write all possible images and take the sum, hoping that the sum will converge. And here it is said like this. One sum of logarithms is like a sum of potentials created by this charges placed on the points of lattice. And another expression is a function that has precisely this zeros. But the principle is always the same. If you manage to write some function that has the same analytic properties, like it has zeros and the same points and the same asymptotics at infinity, then you have basically constructed the same object. So here, for this sign, it is not so obvious because there is some behavior at infinity. But if it is logarithmic derivative, then it is more or less obvious that you construct such a function. Maybe it's obvious for more obvious for logarithm of sign.
La formula che ha scritto viene dal fatto che lui prima la sta usando che più che la tangente abbiamo dimostrato che è quello.
No, no, guarda, cioè sì, lì ci sono poi...
Quando sei d'accordo, però non sei d'accordo con la formula, gli viene il logaritmo del seno di pi grado di 0 su pi grado di z da un lato e dall'altro gli viene il logaritmo della prodotta.
No, inturba questa possibilità di togliere i logaritmi così.
Perché se tu li metti uguali fai la differenza, significa che il logaritmo del rapporto è 0, quindi significa che il rapporto è 1.
Ok, però non lo so. No, magari sono anche convinta di questo, è tutto quello che hai detto dopo, ma non ho capito un cazzo.
Ha detto in generale se tu costruisci due oggetti che hanno che asintoticamente vanno all'infinito, hanno la stessa roba e che hanno gli stessi poli e gli stessi zeri, significa che quando fai lo stesso ordine di poli e di zeri, significa che quando fai la differenza ottieni una funzione omorfa. Se asintoticamente hanno lo stesso comportamento, significa che in differenza vanno a 0. E visto che l'unica funzione che è olomorfa sulla compattificazione di C sulla sfera sono le funzioni costanti, il fatto che all'infinito vanno a 0 significa che praticamente come punto all'infinito questa funzione vale 0 e quindi è costantemente la funzione nulla. Quindi questo è un argomento generale che tu puoi fare. Se tu costruisci un oggetto che ha due oggetti che hanno queste caratteristiche, hai costruito in realtà lo stesso oggetto. E questa cosa, poi in particolare in insieme è importante perché c'è soluzione di tante equazioni che stiamo studiando noi.
Potrebbe anche avere senso, però non lo so, mi sembra tutto un po' interpretato.
Comunque le illustrazioni però c'è.
Sì, ok, i conti, ma tutto.
No, questo si riconduce al fatto delle cariche immagini comunque.
Ah sì, perché da lì avevo capito tutto.
Perché c'è tu le cariche immagini, no, fai questa cosa del logaritmo, perché tu hai calcolato la funzione di Green di una carica. Se vuoi tipo ricondurti al metodo delle cariche immagini, no?
Che non so cosa sia, perché sinceramente non ho capito cosa sia, per quello che fa.
Significa aggiungere tutte cariche fittizie in modo che i dati al bordo del tuo problema rimangono gli stessi. Tipo, vuoi risolvere il problema in una parte, cioè tipo, vuoi risolvere un problema sul semipiano superiore, c'è una carica qua e c'hai che il dato al bordo è che la tua funzione deve essere uguale a 0 qua, su quest'asse qua, ci metti un'altra carica qua, speculare, cioè la stessa intensità però con segno negativo. La somma di queste due cariche ti produce una funzione, cioè tu la sai risolvere in tutto il piano.
Ammettiamo di sì.
Ok? Che cosa significa? Che la funzione qua vale 0 perché cioè, può per simmetria. E c'è però questo argomento lo puoi fare con un numero infinito di cariche.
È quella cosa che mi faceva i quadrati.
Esatto, quella cosa che lui faceva i quadrati. E lui aveva scritto tutta quella serie. Ma il punto è che questa.
E poi ha cacciato fuori che era un fratto seno. Ok, vabbè, se prendiamo questa cosa, allora il fratto dei due produttori di seni
Si riconduce a
questo.
Esatto.
Quindi è contento di sapere questo e capire grazie a questo corso sta cazzo. Ok.
Sorry.
So, can I go further? Do you have some questions? So, I also want to show some phenomenon which is originally related to different equation, to the heat equation, but actually it is it has application to this theta function and also to this ideology to characterize some homomorphic some homomorphic or homomorphic function. We need to know its singularities. So the story is about the heat equation on a circle. So, namely, we are solving this equation ut of t and x equals to dx squared u of t and x, and this u should be periodic. So u of tx plus 1 plus 1 is equal to u of t and x. And we have some initial condition, like u of 0 and x equals u 0 of x. So this problem can be solved by two different methods, well, at least by two. So one method is the method of images. Or we can simply say that there is so you basically need to compute its gain function. So let us say that we are interested actually in this u0 equal to delta function of x. Because any solution can be obtained from this gain function. So we can simply put this unit sources in all integer points. 0, 1, 2, -1, and so on. So the formula for the main function of t and x, and u of t and x, let's put u of t and x, will equal to sum from over integer n's power square root of 4 pi t e to minus t e to minus h minus n square over 4t. Right? And simply sum of all contributions. So, do you use such formula?
Questo è no? Dice
Sì, anche facciamo di sì, io questa lezione non voglio più parlare perché sono assistenti.
So if you apply here this heat equation, it will give a delta function at t equals to 0, and for coordinate it will be all integer points. So if you respect to this fundamental domain, it will have a single delta function at this integer point. So dt minus dxx g equals to sum over the delta of x minus n for n integer. So if, for example, times delta of t. So if x is from minus 1 half to 1 half, for example, the only relevant delta function is delta of x. As always in this matter of images, so all other images which are not in the fundamental domain contribute to the equation and contribute to such periodicity properties in the sense that they make our function periodic. But the only contribution to this delta function comes from a single image in this fundamental domain. We don't, so in this sense, other images are well, they're key images, not real sources. Is it fine? Are there some questions? But yes, so we can get it as the sum of images. The only one thing we need to check, and this actually defines some function in some this series converter. This series converters. But we see that it converters because all the these terms go to infinity very fast. They go to zero very fast, like exponential of minus something periodic. Another way to compute this is to use Fourier models. So if you want to write a delta function, we should write sum of the function in the initial condition. We can write sum over integers e to the 2 I and x. And so how to check the coefficient? We can simply integrate the function from 0 to 1. I and x. Sorry. The delta of dx equals to 1. So this integral comes from the term n equals to 0. Integral for other terms are 0. And again, if you want to check that it is a delta function, then we should write something like minus epsilon of n, take the sum, and study its possibilities. We did this computation at some moment. I don't want to repeat it again. Okay, this delta of x is our u0 of x. So now we look for a solution of this u of p and x as the sum of over integer n, cn, e to the 2 pi I n cn of p, e to the 2 pi I n x. What should be the formula for the cns to give a solution of this equation? And so on. Because of this, we know that u0, so u of 0 and x equals to the sum over integer and cn of 0 e to the 2 I and x. It equals to just e to the 2 pi I and x, because we are expecting to be delta function. So we conclude that this cns of 0 equal to 1, all of them. What do we get if we substitute this u of t and x into the heat equation and solve it?
We get Cn prime of t
Equals.
Equals to minus 4 pi square n square Cn t.
Right. So
And this is Cn t equal to e to the minus 4 pi square n square t.
plus the factor times e to the 2 pi I and x. So there is one formula of this kind, and then there is another formula of that kind. If now if you now write inequality between these formulas, we see from level thickness functions. There is the sum. So that formula can be written in a different form. There's a sum over e to the minus squared over 4t plus nx over t minus 2t squared over 4 t. So to make it similar to something that we already had,
over square root of 4 pi t. Right.
Yes.
Thank you.
So let us introduce the following quantity. Tau equals to 4 pi I. Then this quality becomes a sum over n integers e to I tau n squared e to the 2 pi I n x equals to 1 over 12 minus I tau sum over so here and integers. Let me write this coefficient in front. So the e to
Maybe.
pi I minus pi I x squared over tau, something like this. Sum over e to I minus 1 over tau plus 2 pi I and x over tau. So
No. Okay. 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 You're Ok, sorry. Ah, ok, capito che stai facendo. Prima avevo capito index minus tavolo. Ok.
So, this formula on the left-hand side is very similar to the theta function we already defined. It was called theta 1, and this is called theta 3 of x and tau. And so in the right-hand side, you clearly see that this function equals to theta 3 of x over tau minus 1 over tau. So, and we have this equality that theta 3 of x and tau equals to e to minus 5x squared over tau over square root of minus 5 tau theta 3 of x over tau minus 1 over tau. And I don't want to prove this, but it is quite easy. You can simply regroup the terms and see that this theta 3 of x and tau is proportional to theta 1, the strict argument. So it is proportional to theta 1 of x plus 1 plus tau over 2. There is some linear term and some constant term. So the consequence of this is that zeros of this theta function are here. So it is orthonormal domain, no, 0 over tau, tau plus 1, 1. And here is 0 of theta 3. And 0 of theta 1 is here. There are actually two more theta functions, and their zeros are here. So it's theta 2, and this is theta 4. But that point is over. We have this lattice whose vectors tau and 1. But we can equivalently scale the variable like if variable z is going over such a parallelogram 1 tau variable z. Then a variable z over tau will go over the parallelogram like this. 1, 1 over tau. And we can flip it, of course, so we can write that to make it an upper halfway, we can say that it is 1 minus 1 over tau. Maybe it's better to change this variable. No. It will be kind of an domain. And the point is that this middle point of the fundamental domain should be the same. And the same happens to that point that was at 0. If we do this change of coordinates, we again see some function that has zeros in this lattice. 1 plus tau over 2 plus integer combinations of 1 and tau. And its zeros should coincide with zeros of theta 3. So this function should coincide with zeros of this function. And once the zero coincide, we only need to check that they have the same periodicity properties of this kind. So
sorry, but I don't totally get how do you construct such a different lattice with the edges of
1 and minus 1 over tau.
No, I mean you are talking about another kind of lattice, or I get wrong.
Another it means shifted by 1/2 plus
no, because you draw like not orthogonal.
I've chosen tau to be any complex number. It doesn't matter. You can choose it purely imaginary.
Okay.
Just consider another general situation.
I know, but tau, for how we define it, must be imaginary.
Yes.
And so the lattice is always the same.
No, in our particular situation, it is true in the sense of no, but why is it the same? It becomes a lattice with parameter 1 over tau. So minus 1 over tau. So it changes.
But the lattice.
Oh, so one lattice is something like this. Another lattice is like this. No.
Okay, but it is always orthogonal. I mean.
It had to be orthogonal if we apply this techniques to solve.
Like you have to ask there some different condition, maybe.
No, what do you mean?
I mean maybe if you want to achieve not an orthogonal lattice, you may ask not a that kind of periodic condition. You could ask like u of t plus 1 x plus 1 equal to ut x. That gives you maybe an orthogonal, not orthogonal lattice.
No, something different, I think. Actually, we are thinking about set boundary conditions. It's something involved with time. Probably it is something. I need to think if it can correspond to arbitrary values of tau, but it looks quite strange. It complicates this equation a lot because it is something non-local in time. We should look at some boundary conditions at different time. Here I'm saying a very simple thing, but we can simply consider the analytic definition of this function. We should not necessarily look at it only for purely imaginary tau. It is defined for any tau in our pathway. In some series it is just an discrete equation which forced us to make it purely imaginary. And also in the terms of that problem had some rectangle and it was also purely imaginary, but in general it would be arbitrary. In our way.
Okay.
equal we see in this formula. And if we want to use this heat equation, then we obtain the so-called Poisson summation formula. This is a formula stating that a sum of values of some function and sum of at integer points and sum of values of its Fourier transformation equal. But it's basically a statement that this is a periodic delta function. So we integrate this periodic delta function with some function defined on the whole line. On the left-hand side, will give sum of values of this function at all integer points, and the right-hand side will give us sum of its Fourier components. Yeah. We can write that sum of e to the 2 and x is sum over n integers delta of x minus n. And this is the other function at all integer points. And now we integrate it with some function f. Sum over n dx equals to sum over n f n. Maybe the solve. Do you have any questions about this? Okay, thanks for watching.
Thank you.